But I don't know. You let everyone in. I just said I know what the SQL. Oh, I don't know what invest one. It doesn't invest like. Oh, I see. I got it. You see the shirts. Yeah, they have a little. Yeah, I got it. Okay, cool. I because when somebody an official government, there's really person power. There are not theirs. Okay, so then they are theirs because they're stolen. That's how that works. This is paradoxical. No way. That's awesome, dude. It was like an AliExpress sticker pack. I love it. I'm not gonna lie. From afar, I was looking at that, and I thought that was like some sort of mosaic. Yeah. Yes. I looked closer, and it was still showing this was on that pin. I would say so. It's been at least years since I've consumed any of them.
Good job.
But yes, I am. First time. Twice. Okay. I would have brought back all of the parts that was and part of mine. No, I learned some on my own, and I took some classes, and I practiced a lot.
Can you spare a minute?
Yep.
Awesome. So I'm trying to figure out the time constant for week 2. And they gave me the width of this, which to me seems like a time constant.
Well, what units would a time constant have?
Something per, well, it should be seconds, right?
Yeah.
Okay. But we've been doing over seconds the whole time.
Oh, okay. So
I think we need to take all of them to the negative.
But so, like, what time constant are you talking about? Like,
I've been thinking that's the time constant, but I think time constant's L over R, isn't it?
yeah, so this has units of frequency. So
I should be taking this all to the power of -1 to get my time constant.
yeah, but I guess I'm still wondering, are you talking about like day 1 of the lab?
No, I was talking about week 2 of
does
the lab.
week 2, does it ask you for a time constant? I mean, it might ask you for the width, which is just gamma, and the resonance frequency, which is the omega naught. I guess here, let's see how much time do we have.
yeah, because gamma would be the width of this.
Yeah, that's
Yeah.
definitely gamma. We've been treating gamma as our so it actually is not our time constant.
Yeah, it was the time constant when we had the damped oscillations. Then those damped oscillations decayed with a time constant that was like 1 over gamma.
But that's still hertz.
No, the time constant would be 1 over gamma in that case, which would be in seconds.
Oh, 1 over gamma. Yeah. So I think
Yeah.
take all of that.
So, yeah, 231. Anyways, I'm going to start in a second here, but let me.
I know that. It's so adamant. There are more. There's 2. No. That one, right, there's a guy.
All right. So let's start. What we were thinking about at the end of last time were these op amps or operational amplifiers, and it was a device that had two inputs, and we called them V minus and V plus. V minus would be the inverting input, and V plus was called the non-inverting input. And then it had one output. And the output was equal to some gain factor times the difference between the inputs. And the reason that we call the V minus the inverting input, because if we set V plus to 0, then the output would be minus the gain times the negative, so it would have the opposite sign. Whereas if we set V minus to 0, then the output would be some gain times V plus, which would be a positive or a non-inverting output. The other thing we just realized or just made note of is that the op amp needs to be powered. So it needs to be powered with plus minus VCC. For us, we'll use 15 volts for VCC. So we'll power this thing with plus and minus 15 volts. And that was everything we needed to know. We just made a note of the fact that in most circuit diagrams with op amps, they will usually omit the power terminals in the diagram, but they are always there. The op amps need to be powered. So what we ended with last time were the two golden rules for analyzing op amp circuits. The first golden rule was that the input impedance to the device was very large. And that just means that there's no current going into the op amp inputs. So if we go look at the circuit, the I minus and I plus are currents that are fed into the inputs or maybe coming out of the inputs. Those are always going to be 0. Okay, that golden rule more or less always applies. The second one was we needed a qualifying statement is when we're going to use negative feedback. And negative feedback was going to involve some kind of connection from the output back to the inverting input. So the idea with negative feedback is if there was, say, some kind of voltage fluctuation at the output, maybe the output jumped up suddenly for some reason, then that gets fed back into here and it goes to the inverting input. But if the inverting input, if that voltage jumps up a little bit, the output is proportional to minus the inverting input times some gain. And so fluctuations, positive fluctuations at the output get fed back and the inverting input pulls that output back down. So negative feedback tends to stabilize the output. And so that's why we're using it. The circuit that you're going to build and analyze tomorrow is this one. This is the inverting amplifier. And we're going to start by analyzing the circuit. All we're going to do is faithfully apply the golden rules, and then we'll analyze the circuit using standard methods, Kirchhoff the rules and things like that. So let's start then. Golden rule number 1. All that says is that I minus is equal to I plus is equal to 0. So if we were to draw that on our circuit, we would have, say, an I minus here is going to be 0, and this is going to be an I plus is equal to 0. So that's the first golden rule. So let's see what is the consequence of that. Let's suppose that we had a current I going through R1. So I'll say a current I. Let me just say a current I1. And then let's suppose that we had a current I2 going through R2. And if we do a junction rule analysis, so let's do junction rule at, let's call this junction 1. Okay, so all we have to do is keep track of the total current going into the junction and make it equal to the total current going out of the junction. So we have I1 coming in. And what's going out? In principle, we would have I minus coming out the way that I've drawn it. So I'll put that in there. We're going to set it equal to 0, but let's just write it down. And then we have this I2 coming out as well. So we put a plus I2. But by the first golden rule, this I minus is 0. And so what we conclude then is that I1 is equal to I2. And if those currents are the same, we don't need a subscript. So I'm just going to call that current I. And we'll go back to our drawing here. And let's get rid of our I1 and our I2 and just say that we have a current I that goes through both resistors R1 and R2. This simplifies the analysis a lot because I don't have to figure out kind of what's the ratio of the currents in these two resistors. They have the same current, and that's going to make things pretty straightforward. Okay, so that's everything for golden rule number 1. So we next go to golden rule number 2. And golden rule number 2 said that the voltage at the inverting input and the voltage at the non-inverting input have to be equal. I think I said this last time, but let me just remind you, by far the most common mistake in op-amp analysis is that students say V minus is equal to V plus is equal to 0. That's true some of the times, but it's not true all of the time. What we are saying is that these voltages have to be equal. They have the same value. It's not necessarily 0. Sometimes it will be. In fact, in this case, they are the 0. Because if I look here, I have V plus is the voltage at my non-inverting input, but that's connected directly to ground. There's nothing between V plus and ground except an ideal wire. And so we can say, because V plus has a direct connection to ground, V plus is equal to 0. And then we can say, therefore, by golden rule number 2, it must also be the case that V minus is equal to 0. So it is true for this circuit that the voltages at the two inputs are both 0. And so let's go add that to our diagram here. And so I'm going to say V minus is also equal to 0. And that's the voltage right here at that node. Okay, so that's the application of the two golden rules. And it gives us a lot of information. It tells us that R1 and R2 have the same current and that the voltages at these nodes are 0. It's obvious that this one is 0. The real bit of information that we got is that we have 0 volts sitting right here. And it's going to turn out that with those two bits of information, we can complete the analysis of the circuit. So what we're going to do is we're just going to keep track of changes in voltage. For example, we could start right here at the input where we know the voltage is V in. So maybe we connect like a battery or a function generator here. And so we set some voltage. So we're going to call that V in. And then we're going to cross resistor R1 in the same direction as the current I. So we'll lose a voltage I times R. And that will bring us to this node, which is the voltage at the inverting input. So we can say, let's track the changes in voltage from our input, say V in, to our inverting input V minus. So we start at the input where we have V in. We cross resistor R1 in the direction of the current. And so we lose voltage minus IR. And then we end up at the inverting input. What's the voltage at the inverting input? 0. So that's nice because that makes things simple. So what we could do now is we can solve for the current, and that is just going to be equal to Vn over R. Okay, so we take this to the other side, gets rid of the minus sign, divide by R, and now we know the current. Okay, so that was step 1 in our analysis after doing the loop rule. After doing the golden rules. So let's go back and look at the circuit here. I want to be able to relate the input voltage to the output voltage. What we've done so far is we've written the current in terms of this input voltage. So I want to write the output voltage in terms of that current as well. And then I can build this relationship between the input and output. If this is an amplifier, I'm expecting my output to be some kind of scaled version of the input. And so let's see if that works. So what we're going to do this time is we're going to start at V minus, the inverting input, and we're going to follow the current through R2, and that's going to take us to the output. So we're going to track the changes in voltage from the inverting input, V minus, to the output, V out. Okay, so what did we say? We're going to start at V minus. We know that's 0, but I'll just write it down this time as V minus. We're going to go through R2 in the direction of the current. So we're going to lose voltage IR2. And then we arrive at our output, out. And we already know this is 0. Okay, so V out is equal to minus IR2. And what we're going to do is we're going to take this expression for the current and we're going to sub it in right here for I. Okay, so then we end up with minus. Let's see. We have a V in. What if I think in our diagram, this is R1, right? So I should be labeling this R1. Did I label it R1? I did. So let's make sure we take care of our subscripts. Okay, so we go minus I, and I is V in over R1. So here's our R1, and then this is equal, multiplied by R2. And so therefore we get our final results that we were looking for. I'll write it in this way. V out is equal to minus R2 over R1 times V in. So this is the feature we were looking for. The output is proportional to the input, and the scaling factor is minus R2 over R1. So if Vn is a positive number, then the V out is a negative number. If Vn is negative, V out is positive. That's why it's called an inverting amplifier, because of that negative sign. So this is the inverting part of our amplifier. We often like to talk about the gain of the amplifier, like how much do we amplify our signals by? And so we could say, therefore, V out over V in is equal to G, which we'll call the gain of our amplifier. and that's minus R2 over R1. So it's very convenient because, you know, we have a lot of choice for what resistors we could put in there. And so we can make this gain almost anything that we want. In the lab, lab number 5, so in lab number 5, you will use R2 is equal to 100 kilo ohms, and R1 is equal to 1 kilo ohm. Okay, so then if you take the ratio of those two, you end up with a gain of equal to minus 100. 100 kilo ohms divided by 1 kilo ohm is 100. So if you put in a voltage at your input of, say, 10 millivolts, what you're expecting to get at the output is minus 100 times that. So 10 millivolts times 10 would be 100 millivolts, times another 10 would be a volt. And then with a minus sign, we'd get minus 1 volt. So for Vn is plus 10 millivolts, the output would be minus 1 volt. Okay, that leads us to another, who remembers, what was one of the limitations of the op-amp? What was the biggest possible output that we could get? If we power our op-amp with plus minus 15 volts, what's the most output we could get? Yeah, it's about plus or minus 14. Yeah. So it's slightly under what you're powering. But yeah, that's right. So what that means is in the lab tomorrow, we're going to have to keep the input small. If I had said the input was 1 volt, then I would expect that the output minus 100 volts. But I can't do that. I can only get at most minus 14. So that leads to an effect called saturation. So let's just make a couple notes about that. So recall that the op-amp can output a maximum of about plus or minus V saturation, which is about plus or minus 14 volts if VCC is equal to plus or minus 15 volts. Okay. So what does that mean? That means that V out maximum is equal to plus or minus V saturation. And we know that V out is equal to minus the gain times V in. Okay, so what's the restriction on V in? What's the biggest V in I could put in without hitting the saturation? Well, so therefore we require that minus the gain times V in. Let's just do absolute values. Let's not worry about the signs for now. This has to be less than or equal to V saturation, right? I can't have an output that's bigger than the maximum possible output. And so that means V in must be less than or equal to V saturation divided by the gain. So if our gain in the lab tomorrow is going to be 100 and V saturation is 14 volts, that means we have to keep our input below 140 millivolts all of the time. So let's draw what would happen if we broke that requirement. So I'll draw a V in. We're going to use a function generator to provide our input voltage. And so let me draw it like that. So we get a sine wave as our V in. And then I'm going to draw V out below that. So V out is going to be a scaled version of the inputs. So like so. Let me indicate the zero crossings. When the input is zero, I expect the output to still be zero. So I'll have some points here. Okay, now let's suppose that we have an input that is bigger than the maximum allowed. So I'm going to draw a dashed line here and a dashed line here. And we said we wanted to keep our inputs below V saturation divided by G and above minus V saturation divided by G. Okay, and so we're going to have some special points right here. I'm going to find all of these places where our input is too big. And it's going to be something like this. Okay, so initially, we have no problem. Our input is smaller than the limit that we set. Okay, so that's fine. Oh, I should have extended these down into the negative region. The difference here is that we have an inverting amplifier. So we're not going to get a positive voltage at the output. We're going to get some negative voltage. So we'll start with some negative voltage that looks like this. Let me skip over this section for a bit. And then we go to this section here. And from this time to this time, we're in the allowed range of our input voltage. We just have to invert this. And so that's going to look something like this. So, okay. What do you think is going to happen here in the disallowed region? What's the curve going to look like? Yeah, it's constant. It's going to be just sitting at the saturation voltage, and it'll sit like this, and this will be exactly at minus V saturation. Okay, and then this whole thing will continue. Wherever we get an input that's too large, the output will saturate. So this is also called like clipping. We've clipped the output. All right, and then this whole thing just continues on in that kind of fashion. So we get clipping here, and this has to go through zero, and then we get some clipping over here, like so. All right. So this is saturation of the op amp output, sometimes called clipping. And so you'll see this in the lab. You can easily just increase the amplitude of your input until you observe this clipping. Yep.
Is the in-between section behind clipping still supposed to be sinusoidal?
Yep. Yeah, they are. Yes. Yes. So, I mean, maybe I didn't draw it great, but this is supposed to have the same sort of curvature as this. It's just inverted. Yeah, exactly. Okay, so you will observe the clipping in the lab tomorrow. And so one of the things that you should do is, once you've seen that, when you're actually taking the data that you want to collect, you want to make sure that you avoid this clipping effect. Okay, and that just means you have to turn down your amplitude of your inputs until it's always below the maximum allowed value. So let's suppose I draw another red curve that doesn't cause saturation, and it might look something like this. So this dashed line. And then the corresponding blue dashed line would be one that wouldn't clip, and it would look just sinusoidal. And so again, I may not draw it perfectly, but it would look something like this. Okay, so no clipping. All right. So the other thing I wanted to just discuss briefly today is the packaging of the op amps. Like, what do they physically look like when you use them? So op amps come packaged as a chip. So what does the chip look like? It just looks like a little chunk of black stuff. Okay, so it's a black little square, and then it's got some markings on it. So it has like a little indentation at the top or a little circle in one of the corners. It might have one or both of these markings. And then the other thing it has is it has a series of pins. The op amps we're going to use have 8 pins. So these are 8 pins or electrical contacts. The chip, its size and the geometry of the pins, the spacing of them are designed so that they plug into your breadboard easily. So you don't, all you have to do is you just grab the thing and just push it into your breadboard. The reason that we have these markings, this little circle or this little semicircle indentation, is because we need to count the pins. We need to know their numbering. And the way they're counted is you find the corner that has this little circle or this thing at the top, and you start at the left corner, and that's pin number 1. And then you just count counterclockwise. And so over here, you continue the counterclockwise pattern. And so this is an 8-pin device, and the pins are numbered 1 through 8. All right. The way our op amp sits in here is that, let's see, I want to do a little better than that. So it's something like this. So there's our op amp. Here's our inverting input, and here's our non-inverting input. Okay, the inverting input is connected to pin 2. So this is V minus is pin 2. The non-inverting input is connected to pin 3, and so this will be plus. All right. The output goes to pin 6. So we'll connect the output to 6, and we'll say that that's going to be the out. The only other things that we have to worry about are the power terminals. So over here, we'll draw one of our power terminals. That goes to pin 7. This one is plus VCC. And it's important that it's plus, okay? You can't put the negative voltage there. So this plus 15 volts would go here. Okay, and then the negative power terminal goes to pin 4. And so that is going to be minus VCC or minus 15 volts. We'll go to pin 4. Pins 1, 5, and 8, we will not use. Okay, so that's how the thing's going to come packaged, and that's how you're going to have to connect it when you start working with the circuit board. All right. So let's talk about what you're actually going to measure. In lab number 5, we will use a function generator to provide Vin. So Vin is going to be some amplitude times sine omega t. Okay. So what we'll do is we'll measure the amplitude of, well, okay, let's summarize what we'll measure all at once. Let's continue thinking about what we're going to do. So we'll measure V in and V out. So what's V out going to be? It's going to be an oscillating signal as well. There's going to be a V out. And it's going to oscillate at the same frequency. It'll just be inverted. So I can stick a minus sign out front here. Or if I didn't want to put a minus sign, what else could I do? How do I invert a sign without a negative sign? What if I added a phase of pi? That would shift it half a period and that would invert it. So that would be equivalent. But anyways, we could just put the minus sign out front there. Okay, so then our circuit is going to look like this. We'll have our function generator providing V in. We'll take our resistor, we'll call it R1. We'll have our op amp. The non-inverting input will be grounded. We'll have our negative feedback, like so. And then we'll have R2. And then our output will go over here. So what we'll have is our oscilloscope. And maybe we have channel 1 here. So what are we going to do with channel 1? Well, the grounds all have to be common. So let's just connect the grounds of both channels to the ground of the circuit. Okay, so that's important. And then what we'll do is we'll take channel 1, for example, and we'll measure the input voltage, and then we'll take channel 2 and we'll measure this output voltage. So in fact, what I could do is I can get rid of this line here because we've got our ground connection here. So channel 1 of the oscilloscope will measure the input voltage. Channel 2 will measure the output from our op amp, so V out. Okay. So we will measure the amplitude of V in. And the amplitude of V in is just what I said was capital V. And the amplitude of V out, which we'll use capital V out for that amplitude, as a function of frequency. Right, so where F is going to be the angular frequency divided by 2 pi. So we have a knob on the function generator, and so we can vary the frequency as we like. So what would you think would happen if our gain is just going to be equal to R2 over R1? As I change the frequency, I mean, these resistors don't depend on frequency, so what's going to happen to the gain? It does not change, right? It's just a constant. It's not 1, it's whatever the ratio of these resistors are, right? 100 in our case. So if you actually did that measurement, right? So if we were to plot here as a function of frequency, let's just say the absolute value of the gain. So I don't want to worry about the negative sign. What you would find is as you did the measurements, it would indeed be the case that the gain doesn't change. Whoops. So let me put some error bars in here. And so that's absolutely what you would find and what you will find tomorrow. So at low enough frequencies, the absolute value of the gain, which is just the ratio of the amplitudes of the inputs and outputs is constant. So it's independent of F. Okay, however, as frequency is increased, we eventually reach a point at which the gain decreases. And so let me show you what that would look like. You're going to keep going. Maybe it's still flat a little bit longer, but then you'll eventually find that this gain will start to decrease. Okay, and so put some error bars on here. And so what we're going to do is we're going to try to measure where does the gain start to go down. Now, I've been a bit misleading here. I've drawn this as if I'm plotting the gain versus frequency exactly like that. But the plot will look this way if you plot the log of the gain as a function of the log of the frequency. And so that is the plot that you're going to construct in tomorrow's lab. All right, there's one special frequency here that we want to pay attention to. So we define what's called the bandwidth of the amplifier as the frequency, let me call it F star, at which the gain falls to 1/√2 of the low frequency value. Okay, so what does that mean? What if I said over here that at low frequencies, let me say we were measuring a gain of G0, right? So maybe G0 is 100. At some point, the gain will fall to this G0 value divided by √2. So if G0 is 100, G0 divided by √2 is like 70.7. So 70%. And so if we take a dashed line here and we find where we hit that curve and then extend down, this is F star, and this range of frequencies is called the bandwidth. The reason bandwidth is a useful concept is because it sort of tells you the useful frequency range of the amplifier, right? If I'm below the bandwidth, the gain is mostly flat and so well behaved. If I start getting close to the bandwidth, then I start seeing some change. If I go outside the bandwidth, then the gain really drops quickly. And in fact, what you'll see is even more distortions of the signal. So it won't look like a pure sine wave in all cases. So what the bandwidth does is it tells us the frequency range over which we can use this amplifier and get well-behaved results. So the bandwidth, which is, let's call bandwidth BW, bandwidth. So it's from 0 to this F star that we defined. Defines the useful frequency range over which the amplifier behaves well. Okay, good. Does that make sense? Is there any questions? Yeah.
Is there a reason why it shows large resistor just to get the gain.
No, you could choose sort of like, are you saying, could I choose 1 ohm and 100 ohms or something like that? Yeah, you do have some flexibility there. If I use a really small resistor for R1, then what's going to happen is you're going to get pretty large currents going through your circuit, and maybe you want to avoid that. So bigger resistors just make smaller currents, less power dissipation. Yeah. Okay, so we have 10 minutes left. Let's do one more application. So we'll practice applying our golden rules. So another op-amp application. I'm not going to tell you what this one does. We'll just analyze it and we'll find out. Okay, so it's going to be similar, not too different. So this time I'm going to put my inverting input at the bottom and my non-inverting input at the top. Okay, and so into the non-inverting input, we'll have our input voltage V in. This is going to be our output, V out, just sitting here. And so the part that's a little different is this time our inverting input goes to ground, but it goes to ground through a resistor. It's not a direct connection to ground. Okay, and then here's our R2, and that completes the circuit. Again, we have negative feedback, right? We have the output connected in some way back to the inverting input. Okay, so golden rule number 1. Well, let's see. Let's draw some currents here. I would have like an I plus, but I know that's going to be 0. Okay, I would have potentially an I minus, but I know that's going to be 0 by the golden rule. So I could draw like a current I1 in R1 and I2 in R2, but I know that if I apply the junction rule here, because I minus is 0, these currents are going to be the same. So instead of drawing 2 currents from the beginning, what we'll do is just say, well, look, we're going to have some current I, and it's going to be the same current through R1 and R2. So golden rule number 1 says I minus is equal to I plus, which is equal to 0. And as a result, R1 and R2 have the same current I. Okay, golden rule number 2. All right, so what golden rule number 2 says is there's a node here, and that voltage is V minus, and then there's a node here, and that voltage is V plus. So golden rule number 2 says that V minus is equal to V plus. All right. So what are V minus and V plus equal to in this circuit? It's not 0 because there's no direct ground connection. What's V plus equal to? VN, right? It's just connected directly to our input. So from our circuit, we have that V plus is equal to Vn. So therefore, V minus must be equal to Vn. That's the secret sauce. That's the golden rule. That's what allows us to analyze these circuits in a straightforward manner. So we have a Vn here. Okay, now golden rule stuff is finished. All we have to do is use our standard Kirchhoff tools to analyze the rest of the circuit. For example, we could start at this node, which is at voltage Vn, and we could follow the current through R1 to the resistor, to ground. So let's track voltage changes from the inverting input to ground. All right, so we start at the inverting input. We go through R1 in the direction of the current. So we have minus I R1, and that takes us to the ground, which is 0. And lo and behold, we get I is equal to Vn over R1. So now we know the current. The last thing we want to do is we want to relate the output back to the input. So the way we'll do that is we know the current is Vn over R. So if I could write an expression for the output in terms of the current, then my relationship is done between those two. Yeah.
You don't have to consider the second booster.
We are going to, yeah. We're going to go from V out, and we're going to follow the current through R2 and R1 back to ground. Okay. So let's try that. Let's track the voltage changes from V out to ground. Okay, so we're going to start at V out. Okay, so we start at V out, then we go through R2 in the direction of the current, so that's minus I R2. And then we go through R1 in the direction of the current, that's minus I R1. And so we get V out minus I R1 minus I R2 is equal to 0. And so therefore, V out is equal to I R1 plus R2. And we're going to do the same thing we did last time. We're going to replace I with Vn over R1. And we are going to find, therefore, V out is equal to Vn over R1, R1 plus R2. And so therefore, let's say we want to calculate V out is equal to, I could write this as 1 plus R2 over R1 times Vn, right? So let's take this R1, put it in the bracket. We get R1 over R1 is 1 plus R2 over R1, and then all multiplied by Vn. This is another amplifier because our output is just a scaled version of the input. So this is another amplifier with a gain G is 1 plus R2 over R1. What's the difference between this amplifier and the previous one? What's the major difference? What's the sign? How are the signs of V out and V in related? They have the same sign. So this is called a non-inverting amplifier. So because V out and V in have the same sign, this is a non-inverting amplifier. There's one more difference, and that is, I have 1 minute, so I could tell you the one difference. What's the smallest possible gain I could have with this circuit? What's the smallest number I could make out of 1 plus R2 over R1? 1, right? I could make R2 0, and I could make R1 go to infinity, and I get a gain of 1. Okay, so the inverting amplifier, so the minimum possible gain of the inverting amplifier is +1. Okay, let's go look at the, sorry, did I say inverting? This is the non-inverting amplifier is +1. Let's go back to this circuit here. Where did we actually calculate the gain? Here it is. What's the, like, there's actually no restrictions on the gain here. It's always negative for the inverting amplifier, but I could make R2 a kilo ohm and I could make R1 100 kilo ohms. I could make the gain -1/100. So I could use it to reduce my input as well. Sometimes that may be a useful thing. I can't do that kind of operation with a non-inverting amplifier. What would you do if you wanted to reduce your input, right? You wanted a gain less than 1, but you didn't want it to be inverting. How could you do that? Using the things that we've talked about so far. Yeah, who has an idea? How could I get rid of this negative sign? What if I took 2 inverting amplifiers, one after the other? I make one with a gain of -10, and I make the next one with a gain of -10. And so there I would have a gain of +. What if I wanted to do a gain of +1/100? I would make a gain of -1/10, and then follow it with another amplifier of a gain of -1/10, and I would get a total gain of +1/100. So that's possible by cascading a pair of inverting amplifiers. Okay, good. Thanks very much. So we'll do some of this in the lab tomorrow, and it will be lots of fun.